Hi, how is everybody liking this silent disco experience? It's definitely very weird from up here. Some people have two headphones, so that's something. So I want to tell you that we, the speakers, we only found out about this yesterday when we came in for the rehearsals and all these headphones were here. And at that point, I realized this is a competition. I wish I knew earlier. I did ask them yesterday if I can add more llamas to my slides, but they said it was too late. So there we go. I do hope you will enjoy the talk even without all the llamas. So I am Anca Agape. I am from AI Inference Team at Meta. And I will talk first. I'll tell you a lot about Llama 4 and about distributed inference. And then we'll have Andre come and talk about our core infrastructure and how we evolved it for LLM inference. Okay, let's get started. So LLMs are everywhere today. And they are everywhere in the Meta products as well. You can talk with the latest Llama 4 model through either all the Meta AI integrations in our apps, or through the Meta AI website, or through the newly launched Meta AI standalone app, which is really fun. If you haven't tried it, please check it out. We have more than 1 billion users that are interacting with Meta AI each month. We all know that LLMs and the GPUs they run on are very expensive, and we offer all of this for free. Also, we just launched in beta mode developer access through Llama API. And LLM inference is not only when we serve the model for product use, but it's also used as part of the model preparation process. We have synthetic data generation for pre-training, and also rejection sampling and reinforcement learning for post-training. And online RL is the newest inference use case that is getting a lot of attention right now, and for which we also spend a lot of energy to build the infra that we need. Because when it is used for reasoning models, it is pushing LLMs closer to AGI. And inference is a space that is seeing a lot of growth right now in terms of use cases and flops. And this is why the talks for this year talk a lot more about inference than last year when we were talking a lot more about training. And my team is responsible for serving the Llama models for all these use cases. And our goal is to find the most efficient deployments for all of them, because the GPUs, as I mentioned, are very expensive. And I'll continue to mention this throughout the talk. Now, a challenge that we have is that the Llama models quickly grew in size. So about 2 years ago, we launched the first Llama model, Llama 2, and the largest one had 70 billion parameters. We thought that was a big model. But fast forward now to 2 years. Just a month ago, we launched the Llama 4 models. These have made the switch from a sparse architecture from a dense architecture to a sparse architecture. And the largest one, the flagship Llama 4 Behemoth, has over 2 trillion parameters. And these models are also more complex due to the architecture that they have. We use the mixture of expert architecture for Llama 4. And I will explain this in a very simplified way, since I'm assuming not everybody's dealing with LLMs every day. So the way to think about the MOE architecture is like the model having a team of experts. And instead of using the whole team all the time, as we do for dense models, we have a smart router that will pick the best expert for each piece of the input. And like this, the model is faster and also more efficient, since we don't run all the model parts all the time, but it still gives high-quality results because it chooses the best expert for the job. And we can take, for example, the Llama 4 Maverick, which is our workhorse model that is powering all of Meta AI right now. So this model, it still has a lot of intelligence packed in the 400 billion total parameters, but it is much cheaper, since at inference, we only activate only 17 billion of these parameters. And the Llama 4 models were carefully sized so that we can run the smaller model, Llama 4 Scout, on a single GPU card with int4 weights, and Llama 4 Maverick on a single H100 host with FP8 weights. And this is very important since we proudly open sourced the Llama 4 models. And in this way, the developers can more easily run these models. But running on just a single GPU does not make the most out of these very expensive GPUs, or it does not lead to the best latency. So, and in fact, at Meta, for the main Llama deployments, we do distributed inference, which means that we split the model processing onto multiple hosts. And in order to understand why we need to do this, let's look first at the system bottlenecks for an LLM. So when processing an input prompt, an LLM will do first a prefill action, which will generate the first token, followed by multiple decode actions to generate the next token until all the response is generated. And prefill is very compute intensive since it needs to process the whole input, and LLMs, as we know, they're autoregressive, and that's very expensive. Prefill will take longer to complete. It will depend on the input size, and prefills are therefore compute bound. Decode, on the other hand, they can use the KV cache from the previous step. They only need to generate one token, so they don't need as much compute. They are going to finish faster, but decode is memory bandwidth bound since it needs to read and write the KV cache and also needs to read the LLM weights. But an LLM system will, of course, handle multiple input prompts in parallel. So let's see what happens when we have that. So an LLM can efficiently handle multiple prompts to continuous batching. And let me explain what continuous batching is. You can imagine that we have the operations that are waiting to be executed in a queue. And they can be prefills for certain prompts or decodes for other prompts. And we take the operations from the queue and we put them in a batch that the LLM can execute simultaneously. And you can think about this like we're concatenating matrices, and then we can do math on them together. This is how LLMs operates. LLMs operates in batches. And we need all the operations in that batch to finalize, to complete, until the LLM can move forward and take next operations and execute another batch. Now, prefill, as I mentioned, can take a longer time to complete. And we can end up in the situation like we have here in batch I plus 2, when a long prefill can slow down all the operations that are being executed on that host at that time. And this leads to longer end-to-end latency and poorer user experience. Now, the solution for this gets us to the first distributed inference method. And this is the first one that we actually use at Meta, and we also use it for all the main Llama deployments, which is disaggregating the prefill step and the decode step and have them execute onto different machines. And if we have prefill and decode in different services, then we don't have prefill affecting decode latency. And also, since they're bound by different system resources, it is much better to be able to size them independently. And we don't have operations timeout in the queue, for example, and we can increase the throughput, especially for the decode. So with this, we can greatly increase the throughput, and we can make more out of this, as I said, like this very expensive GPUs. But this leads to more complicated deployments that we now need to manage, because we used to have the model just on a single host, and now we have this split that we need to manage. And we don't stop here, since sometimes we need to also scale out prefill. So as I mentioned, prefill is compute bound, and the compute needed increases very steeply with the input length, as the input length grows. And the Llama 4 models support really long maximum context length, which is amazing. We have 1 million for Maverick and 10 million for Scout. That's absolutely great. But if we were to actually process a 10 million input on a Scout model that's running on a single H100 host, this will take close to half an hour to generate the first token, like half an hour. No user is going to wait that much, right? So then the solution that we have is to use context parallelism, which is a distributed inference method through which we can split the input and have it be executed in parallel onto multiple machines. And this pretty much reduces the latency proportionally. So if we want to reduce like half an hour to a minute, we need 30 machines. But you need 30 machines, which are now in this like context parallelism group. This is pretty complicated deployment because in this group, you have a leader task, and only that leader task needs to receive external traffic. And also these hosts, since we need them all to be up in order to process one request, they are bound by what we call shared fate, meaning that if one host goes down, we need to consider the whole group down until that host is brought back up. So this is pretty complicated. And now let's also look at decode. Let's not forget about decode. So decode, as I mentioned, is memory bandwidth bound. And that is due to the access to the KV cache and also to the LLM weights. For a mixture of expert architecture, the way to scale out the memory bandwidth is through expert parallelism. And this is a distributed inference method through which we can partition the experts onto multiple hosts. And like this, we decrease the memory bandwidth needed on each host, and we also access more aggregated memory bandwidth, so we can increase the throughput on each host. And that is great, because now we can use more of that GPU compute that was basically blocked by the memory bandwidth. So this can lead to higher throughput. For Maverick, you can get even like up to 2x if you do expert parallelism instead of just running on a single host. But this deployment is complicated. Again, with expert parallelism, all hosts receive traffic, and to process a token, a piece of input, we need to choose the best expert for it, and that expert can be on a different host. So then these hosts need to communicate to each other, and this actually leads to a very intensive all-to-all communication. And we really need, for expert parallelism in order to work, we really need this host to be interconnected by this special type of network, the backend network that like Srupa and Peter also mentioned about, that we used to use it only for training, and now it's needed for inference, for expert parallelism, for the MOE models, because we need this like really low latency GPU to GPU communication. So this poses an extra challenge that we never had to deal with for any service at Meta, that we need this collocation into this backend network. And these hosts are also bound by shared fate, similar to context parallelism. Now, if we put everything together, we can have disaggregated prefill with context parallelism and decode with expert parallelism, and each with their own deployment needs. We initially tried to handle all these complex deployment needs in layers above our core infrastructure, basically my team, but this was becoming really unmanageable, especially at scale. So then is when we turned to our core infra team for a solution. And now I'll pass it over to Andrei.
Thanks, Anca. Hi, I'm Andrei from the Twine scheduler team, and I'll talk about gang scheduling, which is our solution for distributed inference. So the Llama inference stack is built on top of our core systems, InfraCloud Service Platform and Twine. InfraCloud Service Platform handles service configuration and management across a broad spectrum of domains. And Twine is our highly scalable cluster management system that is used for deploying all workloads at Meta across all of its data centers. To solve the problems described by Anca, we needed to implement gang scheduling in Twine, where we could use its low-level container orchestration primitives to build a reliable and efficient solution. As part of that, we introduced a concept of a gang to represent a group of tightly coordinated containers acting as a single whole. But before I delve deeper, let me explain a few basics. In Twine, a simple service is deployed as a job, which is essentially a homogeneous collection of tasks. Tasks are deployed as containers running on different machines, and service discovery is provided out of the box for all services running on Twine. A distributed inference workload is also deployed as a service, but its containers cannot be treated as homogeneous because they need to function differently. And more specifically, containers within the same gang need to be able to discover each other and talk over the backend network instead of the front-end one. Load balancing of external requests is done across containers running request-serving code, which, depending on the type of parallelism used, can be all containers of a gang or some of them. And there are runtime dependencies across containers within the same gang. So there are several key features that gang scheduling provides. They are collocation, shared fate, discovery, and routing. Let's talk about collocation first. In the context of Twine gang scheduling, collocation refers to server allocation that takes network topology and failure domains into account. Distributed inference poses a significant challenge due to its reliance on all-to-all communication, which requires the use of high-speed backend networks, as mentioned earlier. There are multiple such backend networks in a single AI-enabled data center, but they are not necessarily connected with each other. This becomes a placement constraint, as containers of a gang must be co-located within the boundary of the same backend network. Another important aspect of co-location is failure domain alignment. Servers interconnected by a backend network are powered by multiple power sources, which we call MSBs or main switchboards. A failure of an MSB is a very unlikely event, but if it happens, it can bring down a significant portion of a backend network's capacity. If containers of a gang were scattered across MSBs, that could result in affecting too many gangs at the same time due to shared fate. To fight with this problem, Twine does two things. First, it collocates containers of the same gang within the boundary of the same MSB. And second, it spreads out gangs themselves across MSBs. So that minimizes the impact of a single MSB outage. To support topology constraints, Twine shifted away from allocating individual fungible servers one by one to allocating groups of topologically connected servers in an all-or-nothing fashion. Now let's talk about server and container shared fate. If you remember, in distributed inference, nodes work collectively to serve requests. From the scheduling layer's point of view, this means that although containers run on different machines, their life cycles are tightly coupled. And that translates to gangs being indivisible units of work, which means that a gang-scheduled workload is scheduled in terms of whole gangs rather than individual tasks. For example, to handle an increased request volume, a workload can be resized by autoscaler, resulting in starting more gangs and load balancing across them. Server and container shared fate is handled coherently. If a single server fails, it results in the entire gang failure, and Twine responds to that by moving the gang over to a healthy group of servers and starting containers there. All sorts of infrastructure events are handled similar to this. Workload management operations performed by users like you and me are handled with respect to the gang boundaries, which means that if a single task needs to be restarted to deploy new binaries or configuration, the control plane makes sure to restart the whole gang. And lastly, if a container crashes due to an application error, the same thing happens. The gang gets restarted. There are certain optimizations in Twine that reduce the overall number of gang restarts within a workload, and that's achieved by bundling planned operations together when it's possible. Now let's talk about the last key feature, discovery and routing. There are two problems solved here. It's intra-gang discovery and load balancing of external requests across gangs. Twine is integrated with SMC, which is our service registration and discovery system. It enables inter-service communication across all of Meta. Gang member endpoints are registered in SMC and labeled with gang identifiers, such as a global unique gang ID. In addition to that, the same set of identifiers is exposed in the container environment. This allows containers of a gang reason about their role within the gang. Containers make queries to SMC to discover peers, and that's obviously needed to establish all-to-all communication within a gang. And because all of the endpoints in SMC are labeled, it makes it possible to route traffic to all or only specific gang members across all gangs of a workload. This allows for flexible policies to be built, flexible routing policies to be built on top of the core discovery mechanics. So we've discussed how we support gangs. Let's take a quick look at how we deploy models. One approach is to map all model partitions to a single job. A single job consisting of multiple gangs, where in each gang, each task would run a different partition. While this seems straightforward, it is not something that really lines up well with Twine's homogeneous job model, because all of the containers here need to function differently. A much more natural approach is to map each model partition to a separate job. That makes model management easier, but it requires Twine to support gangs spanning across jobs. In this model, each gang runs a task from each job, with jobs conforming to strict gang semantics. And this allows Twine to satisfy overall gang requirements. We support both deployment models, but we plan to use the multi-job model going forward. Now, coming back to Anca's original example of complex requirements, we can see that we have all of the building blocks necessary to support distributed inference. The disaggregated LLM from this example can be deployed as two independently scalable gang workloads, with the prefill layer consisting of 2 jobs and the decode layer consisting of 3. And to conclude, building this integration with Twine has led to multiple benefits. For example, it allowed to abstract away the infrastructure details like backend network design. It made it easy to integrate with gang scheduling because everything is still expressed in jobs. And scalability, reliability, and efficiency are inherently the same for gang scheduled workloads as they are for regular jobs. Now, let me turn it back over to Anca so she wraps things up.
Thank you, Andrei. I think I took too long on my first part, but now we get the whole room, so that's amazing. To conclude, we already use gang schedule for Llama 4, without which these deployments would not have been possible. And as we look to the future, we continue to work closest together with our core infra team to try to anticipate the future challenges, because we know there's going to be more challenges due to the model continuing to increase in size, the complexity is going to continue to increase, and also we need to support the new hardware that's going to come. And gang scheduling is just one example on how we are able to quickly evolve our infra to meet AI needs, and we need to continue to do so, as Rupa also said, in order to meet the really massive scale, the huge costs, and also the rapid changes in our race towards AGI. Thank you so much.